Hi, my name is Nova, and I will be your guide today as we explore the sky. Along with the assigned readings, this presentation will introduce you to the sizes and scales in the universe. The learning objective is to grasp the concepts of light speed and actual distances in the cosmos. So let's get started with some of the basics of astronomy. It is important for you to put the three following symbols into your memory bank. The first one represents the speed of light. C equals speed of light, which equals 186,000 miles per second. Next is Ly. This symbol equals the distance light travels in 1 year. This is equivalent to 6 trillion miles. That is a number 6 followed by 12 zeros. Last is AU. AU means the average mean distance between Earth and the Sun. This is equal to 93 million miles, or a 93 followed by 6 zeros. This special distance is called the astronomical unit, or 1 AU. Click on me to see a visual representation of the astronomical unit. Once you are done viewing the image, click on it to return to the slide. The first importance of light and light speed is to understand that when we look out at the cosmos, we are actually looking back in time. For example, light, or rather electromagnetic radiation, travels at the finite speed of 186,000 miles per second, and our Sun is 93 million miles away. If you simply divide that distance by the speed of light, the arithmetic shows it takes 8 minutes for the light of our Sun to reach us here on Earth. Therefore, the light we are seeing right now left the Sun 8 minutes ago, and we are actually looking back in time at how the Sun was 8 minutes ago. Pretty neat. Now let's hear what Professor Quasar has to say about this.
Well, understand this time thing is very, very important because the universe is gigantic. As we look further and further out in the universe, we're looking further and further backwards in time. If a star is 200 million light years from Earth, that means the light we are seeing from that star right now left its surface 200 million years ago and has just reached us here on Earth. 8 minutes ago and 200 million years ago mean the same thing, measurement of distance. And please remind us, Nova, how far away the most distant object that we can detect is?
We can detect objects at a distance of 13.7 billion light years from us. If you want that distance in miles, just multiply 13.7 billion by 6 trillion miles per light year of travel. Then you have mileage. Unfortunately, that number tends to blow up calculators and is why we speak in terms of light years to measure distance in the cosmos.
Also, Nova, the fact is that the speed of light has been known for centuries. And the fact that this speed is finite and constant throughout the universe was part of Einstein's achievement in his first paper on relativity published in 1905. For more information on how we learn to measure the speed of light, see the article attached in the Student Resources section.
The fastest rocket speed we have ever achieved is around 30,000 miles per hour. This speed was reached by the Apollo 11 mission to the Moon in 1969. The Moon is a mere 250,000 miles away, and the trip took 3 days. At the speed of Apollo, it would take 3 years to reach the Sun. Then, you vaporize. The next nearest star to the Earth in the universe is at a distance of 4.2 light years. This star is called Proxima Centauri. The 4.2 light years means that traveling at 186,000 miles per second, it has taken light from that star over 4 years to reach us. Click on the star to see a picture of Proxima Centauri. Once you are done viewing the image, click on it to return to the slide. The fastest interstellar spacecraft is the unmanned Voyager 1 probe. Just recently, in August 2012, Voyager 1 became the first human-made object to enter the previously unexplored region of space known as interstellar space, and at a record speed of about 38,600 miles per hour. Professor Quasar is always ranting that it is cute science fiction to pretend that we can travel at light speed, but the reality is that human spacecraft cannot yet even travel at 50,000 miles per hour. So before we can hop around the universe faster than light speed, we need to be able to move at 50,000 miles per hour. Going 50,000 miles per hour means you could circle the Earth every half hour. This means traveling from Tampa to Hawaii in 5 minutes. So here's the question. If we were to travel at 50,000 miles per hour, how long would it take to reach our next nearest star neighbor, Proxima Centauri? Remember, we learned in the previous slide that Proxima Centauri is 4.2 light years away. We also learned that 1 light year equals 6 trillion miles. Therefore, we need to multiply the distance of the star, which is 4.2 light years away, by 6 trillion miles. When we do this calculation, it shows us that Proxima Centauri is about 25 trillion miles away. Now that we know how far away Proxima Centauri is, let's do some math to see how long it would take for us to travel there. We learned that we have no interstellar spacecraft capable of traveling at 50,000 miles per hour. But let's pretend that we were capable of traveling at that speed. If we were to multiply 50,000 miles per hour by 24 hours in the day, we see that we could travel 1.2 million miles in 1 day. To find the distance we could travel in a year, let's multiply 1.2 million miles by 365 days a year. That tells us that we could travel 438 million miles in 1 year. Remember that it's 25 trillion miles to travel to Proxima Centauri. In order to calculate how many years it would take to get there, let's divide 25 trillion miles by the 438 million miles that we can travel in 1 year. We learned that it would take us 57,077 years of spaceflight time to reach our next nearest star neighbor.
Just imagine any one constellation you can think of, Orion, the Big Dipper, anything, and ask yourself this question. Has the shape of that constellation changed over your lifetime? No. These shapes have not changed for as long as we've been keeping astronomical records. This imaginary permanence of constellations in the sky is caused by the extreme distances involved to these stars. In the upcoming video, if you view and watch the time-lapse motion of the stars as they cross the night sky, you will observe that all of the stars seem to keep their relative distance apart from one another and thus appear to maintain constant shapes as they travel across the night sky.
To properly view this video, go to vimeo.com/1250929 and run it directly that way. We'll move on to the next slide.
The stars of a constellation only appear to be close to one another. In actuality, they are all located at vast distances from one another. Their coherence in the sky is an optical illusion caused by the enormous distances to any stars in the cosmos. This graphic shows you the apparent motion of the immutable celestial sphere. Over the course of the night, stars rise on the east, travel from east to west, and set in the west. From the northern hemisphere, this would appear from left to right. There are only 5 celestial objects visible to the naked eye that are seen to move with respect to the background stars. These objects are the planets. Did you know that planet is the Greek word for wanderer? These 5 celestial objects are named for the Roman gods Mercury, Venus, Mars, Jupiter, and Saturn. Cosmology is the study of the nature, origin, and creation of the universe. The Greek philosopher Aristotle, around 350 BC, proposes his cosmology theory. It is called geocentric cosmology. This means that the Earth is center of the universe and everything in the cosmos revolves around us. The Aristotelian universe can be divided in 2 parts. First is the imperfect, changeable Earth. Second is the perfect heavens, which are described by spheres. Heliocentric cosmology is the correct understanding that the Earth moves and spins around the Sun. This theory would not emerge from the darkness until 1543 and the work of Nicholas Copernicus, which will be covered in Module 3. Ptolemy, around 125 AD, refines Aristotle's theory of geocentric cosmology in his 13-volume treatise, the Almagest. He invents the concepts of epicycles and deference to explain the apparent reverse motion of the planets as they orbited around Earth. Ptolemy's work was the most important treatise on astronomy in the ancient world. It served as the basic guide for Islamic and European astronomers until the beginning of the 17th century. This is an example of a NASA Astronomy Picture of the Day image. The NASA APOD website forms an integral part of our course as we investigate the cosmos.